One scenario that is quite useful for investigating the construction of confidence intervals is the scenario where we're taking a normal distribution and we're interested in confidence intervals for the mean of this distribution, but where we assume that the variance is known, right? So if we're looking at mu in a normally distributed population and sigma squared is actually known, then what this is going to do is going to allow us to focus on the construction of the confidence interval while not worrying so much about the underlying distributions that we need to work with. The reason that this is sort of an easier example to get started with is because if a population is normally distributed and it has a known variance, then the sampling distribution of the sample mean is also exactly normally distributed. So because of this, we can work within the normal distribution framework and we can derive confidence intervals. So first we have to figure out, well, what is the sampling distribution of x bar? If we take x1 through xn to be drawn from a normal population, and we take mu to be unknown, but sigma squared to be known, then we can say that the sampling distribution of x bar is going to be normal, where x bar follows a normal mu sigma squared divided by n distribution. So the mean of x bar is mu, the variance is sigma squared divided by n. Now, we can actually take this one step further and standardize this quantity, right? So the standardized sample mean involves us taking the sample mean itself, so that's x bar, and then we subtract off the mean, right? And in this case, we won't actually be able to calculate this because the mean is not actually known, right? But so we can subtract off the mean and then divide by the square root of our variance or our standard deviation, right? And so the square root of this is going to give us sigma divided by square root of n, right? And so this standardized quantity is then going to follow a normal 0, 1, okay? And the reason that this is going to be useful, we'll see in sort of just a moment here, but the idea is that this distribution, this normal 0, 1, doesn't depend on any of our parameters. And so because of this, this is going to be a helpful way to start working out what our confidence intervals actually are going to have to be. Okay. So using this, we can derive a confidence interval for the mean of our normal population here. So to see how this actually works, we can think about what we want to do with our confidence interval formation. So the first step is that we actually want to find an interval around some statistic, around some estimator that we can say is going to hold with high probability. And the estimator that we're going to use for this, or the one that's sort of most natural to use, is what we're going to call Z. Okay? And what Z is it's exactly that standardized version of the sample mean that we looked at. So it's going to be x bar minus mu, divide that by sigma over the square root of n. Now, we have to be a little bit careful because this is not actually going to be directly computable in itself, right? In order to actually compute this, we would need to know the value of mu. There's other ways of working out what this would have to be without assuming that we know mu, but for now, let's just work within the assumption that we know what mu is, and then we'll see why it doesn't really matter in just a little bit of time. Now, if we were actually able to calculate this, as we had stated on the previous slide, this is going to be a normal 0, 1 distribution. Okay, and so then what we can say is, well, can we find some interval, say probability, such that A is less than or equal to Z, which is less than or equal to B, such that this probability holds, this is that is in this interval with probability of 1 minus alpha. Okay, so we want some high probability. And again, we're thinking about alpha here. Alpha is going to be some value that is something like 0.1 or 0.5 or 0.05 or perhaps 0.01, right? So some small value, okay? So in order for us to do this, we should really sort of think about what it is that we're actually saying. And so we can draw a picture over here. So we'll come in, and the picture that we want to draw is just our standard normal bell curve here. Right? And so this is going to be the standard normal, so that falls at a mean of 0, right? And the idea is that what we want here is we want to find some value A, and the A value is probably going to come down about here, right? And we want some value B, okay, such that the probability that occurs is exactly equal to 1 minus alpha, right? And so if we actually just sort of remember that the probability for any continuous random variable is going to be the area under our density curve, right? Then what we want to say is we want to find values a and b such that this probability here is exactly 1 minus alpha. Okay. Now, importantly, there's going to be a lot of possible values that we could select for this, right? There's going to be plenty of different values that are going to give us this, because you could think about just sort of moving this up or down as we need to. But let's focus in on this for a little bit, and I'll just actually make it slightly larger here so that we can explore what's really going on. Okay. So the idea is that we have a lot of choice over exactly where A and B are going to be, but we want to pick something that seems sensible. And the one thing that we know about our normal distribution is that it's symmetric, right? And so why don't we try to pick a value such that A is just below 0 in the same way that B is going to be above 0, such that this space is equal to this space here. Right? Another way of saying that is that we know if there's 1 minus alpha under the curve, right? Well, then let's think about what is not actually going to be under the curve here, right? So let's think about what is all of this space over here in the shading. And the important thing to note is that if you add up the blue shaded region and you add up the pink shaded region, right? Adding these things together, we know we have to get 1. The probability that you fall anywhere has to be 1. And so we can say that, well, the blue shaded region plus 1 minus alpha, which is what our pink is equal to 1, right? And so then if we actually just work this out, then our blue shaded region has to be equal to alpha, okay? And so that makes sense. If we have alpha plus 1 minus alpha, that gives us our 1. And so then combined between this region and this region, we have exactly alpha. And so the other way that we could think about sort of having equal space is, well, why don't we make it so that down here we put alpha over 2, and up here we put alpha over 2, right? And then by doing that, we're guaranteeing that we sort of have the same amount above and below. We're dealing with the symmetry of the normal distribution in this kind of pleasing way. And so that's exactly what we want to think about doing here, okay? And so I will resize this back down here, sort of move this out of our way, but then we can start thinking about what values can we actually look at there. So in particular, we want a value of A such that there's an alpha over 2 chance that Z is below A, right? So we want to find A such that the probability that Z is less than or equal to A is equal to alpha over 2. Okay. Now, the nice part about this, right, is we can reframe this as phi of A equals alpha over 2, and this is exactly the critical value from the normal. So this is our critical value. You can think about this as being the percentile of the normal. It's been called the critical value for the normal. And in particular, it's the critical value of Z alpha over 2. So Z of alpha over 2 is defined, right? So this is defined to be the quantity such that phi of Z alpha over 2 is equal to alpha over 2. Right? That's what we get by definition in this case. And so we can say, well, then A has to be equal to Z of alpha over 2. Right? So that's our first endpoint here. Now, in terms of our second endpoint, right, we can think about doing a similar thing with B. And so if we come over to our graphic, right, we want alpha over 2 above B. And what that means is we want 1 minus alpha over 2 below B. Right? And so in other words, we want to find B such that the probability that we take B less than or equal to Z, or Z less than or equal to B, sorry, is going to be 1 minus alpha over 2. Right? And so then using the exact same logic that we've done before, this is going to mean that B is equal to z of 1 minus alpha over 2, using the exact same argument that we have here. Okay, and so now what we have is we have our two endpoints here, where b has to be z of 1 minus alpha over 2, the critical value at the 1 minus alpha over 2 level, and a has to be z at the alpha over 2 critical level. Okay, and so then we can actually sort of take this together and sort of form this into the interval that we're actually thinking about. So I'll erase some of the work that we've done here, and then we can sort of get back to finding our confidence interval, right? And so I'll leave in what we have found a and b to be, and I'll leave in sort of the picture that we're working with, but otherwise we can remove sort of what it is that we're doing. And so what we're saying now is that if we take a and b to be those values, well, the probability that z of alpha over 2 is less than or equal to z, which is less than or equal to z of 1 minus alpha over 2, is equal to 1 minus alpha. Okay. Now the problem that we have here is that z is not actually the parameter that we care about, right? And so we have to think about, well, okay, how can we get this to be written as an interval around that parameter? And so if we write out sort of this full expression here, right, we're going to get z of alpha over 2 is less than or equal to, and then we fill in what we have here, x bar minus mu divided by sigma divided by the square root of n is less than or equal to z of 1 minus alpha over 2. Okay, and now what we can do is we can rearrange this so that we have an interval for mu. We want to invert this so that it's an interval around mu. And so the first thing is we can multiply by this sigma over the square root of n. So we get z of alpha over 2 times by sigma divided by the square root of n less than or equal to, we're left with just the numerator here, x bar minus mu, and then we take z, 1 minus alpha over 2 times by sigma over the square root of n. Okay. Now we could subtract from all of these quantities x bar, right? So this is going to be z alpha over 2 times sigma divided by the square root of n is less than or equal to. If we subtract the x bar from the middle, it's going to disappear. We're not going to have anything left, so that'll just be minus mu less than or, oh, and I forgot to include that on the left-hand side here, so we should include minus x bar is less than or equal to minus u less than or equal to z 1 minus alpha over 2 times sigma divided by the square root of n, subtract off the x bar, right? So we've moved the x bar, and now what we have sort of as our final step, right? We have a minus mu in the middle. We don't want the minus mu, so we have to multiply everything through by a -1, right? When you multiply by a negative, you flip the order that the inequalities are going to be looking at, right? And so if we multiply this by a negative, then this term over here is going to become x bar minus z alpha over 2 times sigma over the square root of n, and that's going to be greater than or equal to mu, which will be greater than or equal to x bar minus z of 1 minus alpha over 2 sigma over the square root of n. And so this right here has actually become a confidence interval for us. It's expressed in kind of a strange way here, right? But this is going to be an interval that holds for mu with probability at least 1 minus alpha, right? And so because of that, this is our confidence interval for the mean. So let's just walk through briefly what we did again here, right? We started with this standardized version of the mean, and we know the sampling distribution of that, right? It's a normal 0, 1. And so what we want to do is we want to find, okay, let's get an interval around z, around this statistic that we can calculate, such that it holds with high probability. Right? We're thinking about this in terms of the graphic. We want that area to be 1 minus alpha. And what we said was, let's pick it so that there's alpha over 2 in each of these two different tails down here. Now, because of that, we found out that we had to use these critical values, the alpha over 2 and the 1 minus alpha over 2 critical values. And so then we could walk through, take the interval, invert the interval to get something that's reasonable down here. Now, the one simplification that we can oftentimes make is that with our normal distribution, and this is only going to be true of symmetric distributions, but a, which is equal to z of alpha over 2, is actually going to be the same thing as negative z of 1 minus alpha over 2, right? And if we look at the graphic, this should make a little bit of sense, right? Because what we said is we wanted A to be as far below 0 as B was above 0, right? So the space between 0 and A is the same as the space between 0 and B. It's just A is a negative number and B is a positive number. And so in fact, A is going to be exactly equal to the negative of B. And so we can typically rewrite this interval slightly more cleanly here, where we can rewrite it in terms of the z of 1 minus alpha over 2. And so because of that, if we do this, right, we have negative z of alpha over 2. That is exactly equal to z of 1 minus alpha over 2. Okay, and so what this means is that sort of a more clean way of writing this interval is we're going to have x bar minus z 1 minus alpha over 2 times sigma over the square root of n. That's going to be our lower bound, and our upper bound is going to be x bar plus z 1 minus alpha over 2 sigma over the square root of n. And that's going to be a confidence interval for the mean of a normally distributed random variable if we know the variance, right? Because the only way we can actually calculate this is if we know sigma. All right. And so that process, again, there's a lot of moving parts there, but it gets us to this final result. And that final result is really going to be the most useful of the results that we're thinking about here. It's going to hold no matter what normal distribution we're thinking about. So to summarize that, if we define z of alpha over 2 to be the critical value from the standard normal at the alpha over 2 level, such that phi of z alpha over 2 is equal to alpha over 2, then the standard two-sided confidence interval is given by mu, or for mu is given by x bar plus or minus z alpha over 2, right? And so what we're thinking about here, just again to clarify, right, x bar minus or plus or minus z of alpha over 2 times sigma divided by the square root of n, right? We said on the last slide that this could be written as the same thing as x bar plus or minus negative z 1 minus alpha over 2 sigma over the square root of n. Okay, and this plus or minus, what this means is we're going to take the lower bound to be the smaller of these numbers and the upper bound to be the larger of these numbers. And so that's going to end up giving us x bar minus z 1 minus alpha over 2 sigma on the square root of n, and that's going to go up to x bar plus z 1 minus alpha over 2 sigma over the square root of n. Right, so this interval is the same thing, it's just expressed in a slightly different way. No matter how you express it, that's going to be all right. Now, I'll point out that this is going to take the general form of an estimator plus or minus a critical value times by the standard error, okay, where, again, chi star over alpha over 2 is a critical value of some distribution. In this case, this is corresponding to the normal distribution. And I only point out that this form is taken because this is going to be a very common form for confidence intervals to take. Not all confidence intervals will follow this form, but very many will. And so it's useful to be able to recognize that this is the form of the interval that we're dealing with here. So it's going to be quite common, especially when we're dealing with means and proportions and other common statistics. But other intervals can meet the criteria of our confidence interval beyond this one that we've specified here, right? And so beyond just what we've dealt with for this, there are other possible intervals that we could have found. Okay. And so in particular, we could have formed one-sided confidence intervals, or we could have formed asymmetric confidence intervals. And so what we're thinking about here is instead of taking that 1 minus alpha and putting it evenly right in the middle, we could have taken 1 minus alpha and put it anywhere under that curve, right? And so if you say, okay, well, we're only going to take the lower half of this curve, right? You get 1 minus alpha there, that's going to give you a different interval. Or maybe you say, I don't care if A and B are the same size apart, right? Then you could take A to be some value and you can find B relative to that value, right? And so there's many possible confidence intervals as long as it fits the definition, which is that it's an interval that holds with some set probability, then it's going to be a valid confidence interval, just that some are going to be more useful than others in practice. In general, as long as you're following this general procedure, or it's fitting the general definition, then that's going to be a confidence interval for the parameter that you care about. In general, the reason we're focused on these two-sided symmetric confidence intervals is because they're the most practically useful. They're going to be the narrowest interval for any specific level, and so they tend to be used the most in practice. But there are other intervals that come up, and these intervals may be just as valid and perhaps useful given the specific situation. So it's worth pausing and taking a look at an example here to make sure that we can work through the actual computation of an interval. So we have a medical researcher who wants to estimate the average heart rate of patients after a specific surgery. It's known that post-surgery rates are normally distributed. Standard deviation is 10 beats per minute. Random sample of 36 patients is taken, and their average heart rate is found to be 85. And so it's useful for us, in order to calculate our 95% confidence interval, to start thinking about, well, what are all of the terms that we need? Okay, and so the first thing is that heart rates are going to be normally distributed. Right? And because heart rates are normally distributed, it means that we can use these normal-based confidence intervals. We're told that there's a standard deviation of 10, and so this is our population standard deviation, right? So this value right here, that is what we're taking to be sigma. Okay. A random sample with size 36, right? So n is going to be 36, is found, and their average heart rate is 85 beats per minute. Okay, and so all of the information that we need here is going to be there. We want a 95% confidence level, which means that alpha is going to be 5%, right? So alpha is always 1 minus the confidence level that we want, right? So if we take 1 minus 0.95, that's going to give us our confidence, or our alpha level, okay? And so we can actually extract out all of this information here, right? So the population is normally distributed. We found the sample mean is 85. Sigma is going to be 10. N is 36, and alpha is 1 minus 0.95, which gives us 0.05. Now, in order to actually get our critical values for that, remember that we want the critical values for z of alpha over 2, or equivalently, z of 1 minus alpha over 2, right? And so that's alpha over 2 is going to give us our 0.05 over 2, which is 0.025. Right? And so then we can get our z of 0.025 is negative 1.96. Now, we could have also used, say, z of 1 minus 0.025, which would be z of 0.975. And if you find that, then what you're going to find is that is equal exactly to 1.96. Right? So it's just the positive version there. Either value is going to work in the interval. In this situation, what we've done is we've actually used R to find this, and the R command to find the confidence, or to find the critical values, is going to be qnorm, right? And so with qnorm, you then pass in whatever you want here. So we want 0.025, right? But if we had run instead qnorm of 0.975, then this would have given you 1.96 as the output there. Right? And so again, you can turn to statistical software to actually find what these values are. Okay? But with all of this information, we can then just plug into the formula that we have, right? So we know that we want our confidence interval to be x bar, right? So that's going to be 85 plus or minus, and then we need to take our critical value, so that's going to be 1.96. Because we're adding and subtracting, it doesn't matter if we have the negative sign there or not, right? And then we multiply that by the sigma, which is 10, divided by the square root of n, which is 6. Right? So this is going to ultimately be the confidence interval that we take once we've identified the information here. So x bar plus or minus 1.96 times by sigma over root n is 85 plus or minus 1.96 times 10 over the square root of 36. And if you find the endpoints of that, so you get the first one by subtracting, it's 81.73. You get the second one by adding 88.27, and then together, those are forming the confidence interval. Okay, so normal-based confidence intervals for the mean, they come up quite often, and they're a useful way to start testing out the ideas of confidence intervals. The main drawback to a normal confidence interval is that it requires the population variance, and very often we're not going to have the population variance. If we don't know the mean, we probably don't know the variance, and so because of that, these aren't typically going to be the most applicable in practice. However, all of the ideas that are required to find these intervals are going to be useful for means in other situations where maybe we are not assuming that it's normally distributed, or maybe it's normally distributed, but we just don't know what is the variance. And so because of that, we can build on the same set of ideas here in order to build confidence intervals in situations that might be a little bit more realistic.